Here we go. Unit 4, Lesson 1.2 In the Balance. Our essential question is, what happens when multiple forces act on an object? So like we discussed in Unit 4, Lesson 1.1, forces have magnitude and direction. So we can show magnitude using arrows, and the size of the arrow will tell you the magnitude or the strength of the force. The arrow will also tell you the direction that the force is in. So if we had some arrows, A, B, and C, we know that the size of the arrow tells us the magnitude of the force. So if we were going to rank these according to the least amount of force to the most amount of force, we would put A, and then C, and then B, because A has the shortest arrow, C has the next shortest, and B has the longest. We would also know that all of the arrows, the force was to the right. So here we have an example of where the object was going 10 meters to the right and then changed directions and went 6 meters to the left. You can see that the red arrow is larger and the little arrow is smaller. This is just showing you vectors. So if vectors go in the same direction, they add together. And if they go in opposite directions, they subtract from each other. So in this example, the object traveled 10 meters away from the starting point and then changed directions and went 6 meters towards the starting point. So here you can see the size of the arrow changing. And that is going to represent the change in the force in the spring. And so we get the spring that goes out to here. So at this point, it has the most potential energy, the point that it stops and goes back this way. You can see that the force is increasing and decreasing. So here the pull is the largest. So the arrow has to do with magnitude, the strength of the force. So we have to know a little bit about vectors. And so we have the beginning, we have the end. That's always going to be important to determine how far or the strength, and then direction. So for forces, we have to know what is the magnitude or the strength, and what direction is the force acting in. If we look at a chair, and we have our stick person sitting in a chair, this is a poor stick person with big long legs, but the chair is pushing up on the person, and the person has a force that's going down. And so they are equal, or either the chair would break or the person would go higher in the air. So when the force is equal, there's no motion. So here are some examples of forces. And so we have an airplane, and whoa, when the forces are going, well, actually, this isn't for force, it's just vectors. So this is just the velocity of the plane, showing you how vectors add. So here we have a tailwind in which the plane is going 150 miles an hour and the tailwind is adding to the velocity of the plane. So since they're both in the same direction, they add. If we had a headwind, that's going to be a wind pushing against the plane. That's going to be a subtraction. And so in reality here, the plane is going 120. So this over here is more complex. Just know that when vectors are in the same direction, they add together, and when they're in opposite directions, they subtract. And don't forget that a force is a push or a pull. What's a force? A push and a pull. I wonder if that'll be on the test. I bet you it will. A force is a push or a pull. The formula for force again is a Newton equals a kilogram and how much the kilogram is being accelerated. So force equals mass times acceleration. So we'll talk about what's going on with these formulas, but there are relationships. And so it's when you're looking at a formula, it's good to know that if one side goes up, what happens to the other side? Is it directly proportional? Meaning if acceleration goes up by 1, does the force go up by 1? Or does it go down? So a force diagram shows the forces on an object. And so you can see the stick man. He's pushing a box. And we'll talk about all these forces as we go along. So we have a frictional force that's working against the stick man moving the box. We have the weight of the box being pulled down. So weight is actually a force caused by gravity. We have a normal force, which is the earth pushing up against the weight. And then we have the force due to the acceleration. So when we talk about the net force, it's the combination of all the forces acting on an object. So remember, if the forces are in the same direction, they're going to add together. So notice the size of these arrows, they're different. So since force is a vector, it has both magnitude and direction. So the size of the arrow tells you about the force. And so since this person, let's say he's applying 5 newtons, let's say every person can apply 5 newtons. If there's 2 people, we have 5 newtons plus 5 newtons. So here we would have 10 newtons of force. So each person's force here is going in the same direction, so they add together. So when you look at force diagrams, you are going to add the ones that are in the same direction. And so here you can see the example. This would be maybe we have person 1 that pushes with 2 newtons, and we have another person who's stronger and they push with 3 newtons. And if we add them together, the net force on the box is going to be 5 newtons to the right. When the forces are in the opposite direction, you subtract them. And you're always going to subtract the bigger force from the smaller force. Oh, I thought that was an animation. So when they're in opposite directions, so let's say this is 2 newtons and this is 5 newtons. We know that we're going to end up with 3 newtons to the right. So when they're in opposite directions, you write the bigger force first, and then it tells you what direction the resulting force will be. So here you have 5 newtons to the right and 2 newtons to the left, which ends up being a total force of 3 newtons to the right. So work this one out on your paper. The question would be, what's the net force? And what direction is the force in? Notice that the sizes of the arrows are different to show that magnitude piece. And so since they're in the same direction, we're going to add 3 newtons to 5 newtons. And so the net force on the box would be 8 newtons to the right. How about this one? Try this one on your paper. So to figure the net force, we write the bigger force first. And I always like to write what direction they're going in. That just helps me. Minus 2 newtons because they're not going in the same direction, so they're going to subtract. And so that gives me 4 newtons of net force on the box to the right. So there can be more than 2 forces acting on an object at the same time. Oh, and these can be balanced or unbalanced. And we're going to talk about the difference between balanced and unbalanced forces. In balanced forces, there's no change in the object's motion. So the object is going to be at rest. So if we had a box, and let's say I'm pushing on this side with 3 newtons, and you're pushing on this side with 3 newtons, since the forces on the box are the same, the box isn't going to move anywhere. They're equal. Not only are they equal, they're also in opposite directions. And when we're talking about balanced and unbalanced forces, you got to be talking about the same object. So balanced forces, no change in motion, not moving, equal in size, and opposite. So in this example of tug of war, since the rope isn't moving, the forces are balanced. So when you have a tug of war game and it just seems to stand in one spot, that means that each team is exerting equal amounts of force on the rope. The moment that one team exerts more force, or maybe the other side loses grip, so that reduces the force, then it's going to be not balanced anymore. So here's an example. You have one elephant pulling to the right. You have one elephant pulling to the left, and they're both pulling at 200 newtons. So they're not going to go anywhere. This piece of wood is going to stay right where it's at until the force of these 2 elephants pulling in opposite direction breaks the wood, of course. But in this instance, they are forces that are 0 because they're equal and opposite in direction. Now we go to unbalanced forces. In unbalanced forces, you get a change in speed. And so an object can start moving, it can speed up, or it can slow down, or it can change direction. So if we go back to the box example, and I'm pushing with 3 newtons, and there's 3 students on this side pushing with 10 newtons. The question is, are the forces balanced? No, because the forces are not equal. 3 newtons does not equal, I don't know why it's lagging, 10 newtons. And so what we're going to do is we're going to find the net force on the box. And so we have 10 newtons to the left minus 3 newtons to the right. So this is to the left and this is to the right. And that ends up being 7 newtons to the left. So that means my box is going to move to the left. The bigger the difference is, the faster the object's going to move to the left. So now in our tug of war, you can see that the balances become unbalanced, the forces become unbalanced. So you have them going back and forth where the 2 people win, the 1 person wins, and then the 2 people let go of the rope, which causes a definite unbalanced force and causes all the motion to go to the right. So unbalanced forces. The motion of the object is going to go in the direction of the greater force, and you're going to find the net force by subtracting the 2 forces. So in this example, make a guess on who's going to win this tug of war. Is it going to be the dude in the blue and the chick in the red, or the dude in the gray and the chick in the orange? So the net force on a rope is going to be 500 newtons minus 450 newtons, which gives us 50 newtons to the right. So it's going to be the chick in the red and the dude in the blue that's going to win the tug of war. And that brings us to our questions. Number 8 asks that as you read, underline how one determines the net force. So here we have when they're the same, you add, and when they're different or the opposite, don't know why my pen is lagging, you subtract. And you can see where you need to underline. Okay, the next question says, calculate the net force acting on the appliance box and use it to determine if the box will move. So we have to ask ourselves first, what's the net force on the box? And so we have 210 newtons to the right. Well, we shouldn't put it there. Let me reset. To the right, minus 190 newtons to the left. And so that gives us a net force of 20 newtons to the right. So will the box move? Yes. How do we know? Because the forces are unbalanced. I don't know what's going on. So first thing you do is find the net force. And then since the force is not equal, that means they're unbalanced. And the object is going to move in the direction of the larger force. The box has a net force of 20 newtons on it, pushing it to the right. Number 10, The arrows in the first image show that the forces on the rope are balanced. Draw arrows on the second image to show how the forces on the rope are unbalanced. So we know that there's going to be more force here because all the kids seem to be about the same size. And we know that it's past the beginning point here. And so there's a smaller force here. So we know that it is going to move to the right. Make sure that you take into account size of your arrows when you're drawing arrows, because remember, force has both direction and magnitude or strength. Okay, so I put this in your notes page. So what you're going to do is that if each block equals a Newton, how much, well, I didn't want to do that. So how much force is there? I don't know why it's doing this. How much force? Okay. How much force and what direction is it going in? So let's do one together. One starts here, so there's 1 Newton, 2 Newtons, 3 Newtons, 4 Newtons. So 4 Newtons, and the arrow is going to the right. So finish up the rest of them in your notes. Some forces that we experience in our everyday life is friction and gravity. So friction acts on the direction opposite of the object's direction of motion. So the little piggy is going downhill this direction, and friction is acting against it in this direction. But there's something different about the sidewalk in that it has a coat of ice on it, which has less friction than a dry sidewalk. So friction is always opposite of an object's direction of motion. So here, oh, I didn't stop in the right place. So you have friction acting in this direction, and the horse is going this direction. So when the horse plants its feet down like that, it increases the friction, and it's kind of like a brake, like on your car. So the horse is increasing the friction to allow him to stop by the end of the lane. Friction is caused by the surface of the two objects that are being rubbed together. If we could zoom into the surfaces, like our eyes were like little tiny microscopes, we would see that all surfaces have texture, which they have bumps and jagged edges. And when things have those bumps, they get caught, and that's what causes friction. And there's two types of friction. You have static friction, and static friction is what's going to cause something not to move. And then we have kinetic friction, which would be against the motion of the object. So static friction occurs when objects are not moving, and this force keeps the object from moving around. So if you want the object to move, you have to overcome the weight, the force that's pushing down, and also the friction between the object and whatever surface it's on. Same thing with kinetic friction. The larger the friction is between the two substances, the more force you're going to have to apply to get the object to move. So we have sliding kinetic friction. We have rolling kinetic friction. And we have fluid kinetic friction. So you've heard about if we dropped a bowling ball and a feather from a roof, which one would hit first? Well, the bowling ball is going to hit first because it has a smooth surface and has no air resistance, versus the feather, which has, things that it has it's a structure developed or evolved to promote air resistance so that a bird can fly. So that's why it falls last. If we did this on the moon, however, where there's no air, more or less a vacuum, then when they would both fall at the same time. We can reduce friction by making a surface smoother. So we can do that by applying oil or wax or soap. If you've ever got a ring caught on your finger, it was too small, but you got it on and then you can't get it off. One thing you can do is put some oil on your hand or some soap, and that will help to reduce the friction between the ring and your finger, so hopefully it can slide off. We also may want to increase friction. And so we don't want to be there to be little friction when we're walking across the floor. We just slide around all over the place. And so what we do is we have grip on our shoes. Runners will have a different kind of grip depending on what type of runner they are. A hiker is going to have more grip on the soles of their shoes than someone who's going to do the 50-meter dash or the 100-meter dash. They're going to want to have less grip on their shoes. We throw sand and gravel on icy roads to help increase friction, to help keep cars from sliding around. If you watch any kind of race car, they will change their tires depending on what the racetrack conditions are. So they might have a set of tires for a wet track, a dry track. And so we can change the amount of friction there is by changing the surface. We can also add more mass to an object to keep it from moving. That would increase the friction. So we go back here to our force diagram. And remember, you can have more than one force that's acting upon an object. So we have the force of the stickman pushing to the right. We have the force of friction, which is against motion. It's against between the box's surface on the bottom and the floor. We have the force of the weight of the box, which is the force of gravity. And then we have the normal force, which is the earth pushing against the box on the surface. Gravity is the other force we can't live without. And anything that has mass has a force of attraction to anything else that has mass. So the hair on your head, believe it or not, doesn't have a lot of mass, but each hair on your head is attracted to the hair on your head. But it's so small that we don't notice. But we do notice the gravity of the earth and the moon and the gravity of the earth on us. So gravity is an unbalanced force in that it always is going to be pulling objects back to it. And it pulls with an acceleration of 9.8 meters per second. So you can see how the velocity changes as the ball goes up in the air and goes down in the air. So gravity is always pulling things back to the earth with an acceleration of 9.8 meters per second. Terminal velocity is when the upward force of air resistance equals the force of gravity. So instead of going 9.8 meters per second to 19.6 meters per second, it's going to go at consistent velocity. And so this is a bunch of skydivers that are at terminal velocity and terminal acceleration, and they make these structures or pictures or graphics in the sky. And so this one had 217 of them making this diagram in the sky. I don't know how that's possible. But they are at terminal velocity. So the universal law of gravity, any object with mass is attracted to any other object with mass. Some things that affect mass are distance and the mass of the two objects. So you have this slide here that breaks down the equation for universal gravity. So it depends on two things, mass and distance. The more mass an object has, the larger gravity it has. The smaller the mass, the smaller amount of gravity. So there's a direct relationship between gravity and mass. You increase mass, you're going to increase the gravity. And this force caused by gravity is called weight. So weight is the force of gravity on mass. Mass goes up, the force due to gravity goes up. Distance. Distance isn't quite as straightforward, but for us, all we need to know that is as distance decreases, gravity increases. As distance increases, gravity decreases. So it's inverse. So as distance goes up, gravity goes down. So if you want to think about this, the farther something gets away from Earth, the less Earth is pulling on it. And there's actually a spot outside of the Earth where it's called the escape line. And so once an object gets past there, it has escaped the pull of Earth's gravity. So when we launch a rocket into space, we have to launch it fast enough into this escape area to where Earth isn't pulling it anymore. So it's inversely proportional. So don't worry about the graph. Just know that as distance increases, gravity decreases. Looking at another free body diagram. So instead of the square for the box, you can see the friction is going opposite of the motion of the car, and the thrust is generated by the engine, the weight of the car, and the force of the earth pushing back against the car. You can see the size of the arrows here. And that's the